Ladies and gentlemen, welcome back to my e-learning course on equilibrium of materials. Today we have lecture number 5. You remember during the first lectures we made a really large introduction. We talked in details about the system of quantities, then about chemical fundamentals, and finally about physical fundamentals. But today we really start considering basic concepts of cathode. These are the components, the phases, the system, and we will discuss material balance and concentrations. So first let me talk about the components. In the simplest case, the components which we want to study are usually selected from the list of the stable elements, and this is something we engineers can decide, okay, maybe our bosses. We denote the number of components as capital C, and it's obvious that the minimum number of the components should be 1. With 0 components there is simply nothing to study. On the other hand, the maximum number of possible components is 81, which is, you remember, nothing else as the number of the stable elements. We also use a general symbol for a component, little I, but sometimes we want to make a difference between different components, and then we use capital A or capital B. Capital A and capital B are still general symbols for the component, but then we also can be more specific, and in this case we usually use chemical symbols for the elements, such as aluminum Al or Si for silicon. Now it should be understood that our simplest choice, that the component is equivalent to an element, is fine only for those people who want to study metals and alloys. In this case, the 81 stable elements are actually independent by definition. And this is so because, you remember, in material science engineering we don't touch the nuclei. Therefore, we don't make any nuclear reaction, so the elements are given to us, we never change them. However, for people who are working for polymers and ceramics, it is a more reasonable choice if they select components as compounds. Now, in this case, the choice of the components is not that simple as in the case of the elements. First of all, this is because sometimes chemical reactions can be written between different components, and if that happens, it means that this choice of the components is not good enough, because we have to select a list of independent components. For example, if you want to study water, in principle you can select hydrogen and oxygen and H2O as free components, but this goes against the principle that the components should be independent, and they are not independent because you can write a chemical reaction between them, 2H plus O equals H2O. Of course, the same story if you replace H as an atom by H2 as a molecule, or if you replace O as an atom by O2 as a molecule. Anyway, you are not allowed to select at the same time H2 plus O2 plus H2O for the same reason. However, you can decide to select any of the following cases. For example, you can consider water as a one-component system, or you can consider it as a mixture of hydrogen and water, or as a mixture of oxygen and water, or even as a mixture of hydrogen and oxygen. Another example, if we are interested in iron, oxygen, titanium system from point of view of the ceramist, then we have the following compounds: FeO, Fe2O3, Fe3O4, TiO, TiO2, Ti2O3. But this is too much, Here we have 6 different oxides, and obviously you can write different chemical reactions between them. That is why I actually introduced the component rule. Now, by the way, the phase rule will be given later. It is after Gibbs. It is known widely, I mean the phase rule. It is about the maximum number of possible phases in the system. But this is the component rule. It's not widely known at all. It's introduced actually now. And what I claim is the maximum number of independent components in a system is the number of the elements taken into account in all the components. Well, if we treat components as elements, then this component rule doesn't give anything to us. But if we treat components as components, then the component rule might be important. For example, in the previous example, with considering the iron, oxygen, titanium system from point of view of ceramics, you see we have 3 elements, and therefore the maximum number of independent components must be 3. So for example, from these previous list of oxides, which are 6 oxides, you are allowed to select only 3 of them. For example, a possible list is FeO, Fe2O3 and TiO2. Of course, your actual list can be different from that. This all depends on your interest of your study. And as for laws from this example, it is quite common, at least for polymers and ceramics, that the number of possible components is usually higher than the number of independent components, which is the number of the elements in the components. And then what to do with the rest of the components. So here we selected, for example, 3 components, but we had 6 oxides, so what to do with the rest of the 3 oxides? Well, in this case, the rest of the 3 oxides are not independent components, but they still can be species and they still can serve as bases for different phases. Now let me show to you the same periodic table as I showed before, but this time I show to you only the chemical symbols for those 81 stable elements which can be used by us, materials and metallurgical engineers. You remember element number 1 is hydrogen, element number 83 is bismuth, and we have 2 problematic elements here which are radioactive. That's why we have 83 minus 2, 81 stable elements. And all the elements after bismuth, starting from number 84, all of them are radioactive. They are useless for us. In the previous lecture, we actually discussed isotopes. And now you can ask me a question, what about isotopes in terms of components? Can an isotope be selected as a component? And my answer to this is that usually not. Usually we consider element as a component or compounds made of the elements. And usually we mean that that element which we select as a component is a natural element. It appears as it is found in the Earth crust, including all the natural isotopes of it. Okay? There is maybe one exception from this rule, and this exception is if you are specifically interested in the isotopes. So then, of course, you can make a choice that you select different isotopes of the same element, but this is a very much exceptional case, and in this course, at least at the beginning, it will not be discussed. But then, even if we neglect the isotopes, as explained right now, we have a problem, because you remember we have 13 or at least problematic elements, the most problematic being lithium, because the isotope concentration and therefore the atomic mass is uncertain in the Earth crust. And that is why the sentence I said before, namely that we select elements as components and we mean all the isotopes as they are found in the Earth crust, so this sentence doesn't work for these 13 or at least 6 problematic elements, simply because we cannot say that whatever we find in the Earth crust is well defined, simply because it is not well defined at all. Because in different parts of the Earth crust we find different isotope contents. So now we have a problem here. I can tell you that to my best knowledge at the moment, which is spring 2020, this problem is mostly neglected by the comfort community. But I think that sometimes later this problem should be discussed and resolved, and I expect that later the molar mass, at least of these problematic elements, can be considered a state parameter. Because today, or at least so far, or at least like 15 years ago, molar masses or atomic masses were considered as constants of nature. But it's obvious that they are not constants of nature. At best, they are constants of the Earth crust. But for those 13 problematic elements, they are not constants for the Earth crust. But this is the situation today. So for the time being, what I can tell you, that isotopes are mostly neglected from consideration during the comfort calculations. Now let's talk about the system. This is the system we study. In the simplest case, it is just defined through its components, so it was actually defined before in the previous slides. So I can define the system to be considered as a C-component system. I can call it a one-component system, or a two-component system, or a three-component system, etc. But be careful, the more components you take into account when you define your system, the more complicated and time-consuming your calculation will be. So your choice of a system should be an optimum choice. You should not select too few components, because then you might lose the point in the calculation. On the other hand, you should not select too many components, because then it will become unreasonably difficult. And by the way, when you select the system, you can also select it or name it specifically. For example, you can call the system like the aluminum silicon system, meaning it contains two components, specifically aluminum and silicon. Now, on the other hand, the system can be also imagined as a part of a three-dimensional part of the universe, which is separated from the surroundings. It's separated, of course, by some interface. From this point of view, I mean from the point of view of the communication between the system and the surroundings, we have three different names for the system. The system can be an open system. This is when both materials and energy or heat are allowed to transfer from the system to the surroundings or back. Or the system can be a closed system. In this case, the communication in matter is not allowed. I mean, matter cannot leave the system to the surroundings, and matter cannot come from the surroundings into the system. You know, in opposite case, if the system and the surroundings can change matter, it means that you practically study the universe, which is really not practical. So usually we limit ourselves in studying closed systems, but by the way, in the closed system, energy can still be transferred. This is because through the walls, through the physical walls, which conduct heat, of course, heat can escape or heat can come back, depending, of course, on the temperature difference between the system and the surroundings. And then we have the so-called isolated systems. Now, in the isolated systems, nor energy or heat, neither matter is allowed to transfer from the system to the surroundings or back. And of course, this isolated system is quite imaginary. Now, we engineers can freely decide the amount of each component in the system, which is denoted as Ni. So N, you remember, is amount of matter in moles, and the small symbol I here means component I. Then, of course, we can also add all the amounts of matter of all the components in the system, and then, not surprising, we get the total amount of matter in the system, denoted only simply as N. And based on Ni and N, based on the ratio, we can define the average mole fraction of component in the system, which is dimensionless because it's mole per mole. So this is defined Xi, it's denoted as Xi, small xi. It is defined as the amount of matter of component I in the system dividing by the total amount of matter in the system, mole per mole, dimensionless. Mole fraction, average mole fraction in the system. And then, if you add all of them, all the xi's in the system, then obviously you get 1. And this is simply because if you are adding all parts of anything which is full or the whole, then you get the 100%, which is 1 in fraction. And from here you can get a very important rule, and the very important rule is that in a C-component system it is sufficient to provide information on mole fractions of only about C-1 components, and this because the mole fraction of the last component of the Cth component can be easily calculated as 1 minus the sum of all the others. For example, if you have a two-component AB system, then this equation becomes XA plus XB equals 1, and from here you can express, for example, XB as 1 minus XA. So if XA is given as like 0.8, then XB is usually not given, but all of us know that obviously XB is 1 minus 0.8, which is 0.2. By the way, Xi as a fraction is defined between 0 and 1. And finally, in a one-component system, we have only a single component, then then the mole fraction of this single component is by definition 1. Okay? Well, it's not surprising, of course, that if the system is made of only one single component, then the mole fraction of this component is 1. And that only means that if we will study, when we will study the one-component systems, we will not specify how much is XA because it's known by definition. Let me come back a little bit to the question of state parameters. You remember when we were discussing the ideal gas law, then we actually already found or defined two independent state parameters, which was pressure and temperature. And that time we discussed what is state parameters. State parameters are those physical quantities which are given by us engineers. We can decide which pressure, which temperature we should use for the given experiment. But only those are important state parameters which actually have an influence on the equilibrium of materials. And now we have an additional state parameter because obviously the average composition will be also will have also an influence on the equilibrium of materials, and it also can be given by us because this is me, the engineer, who can decide how much of A and B components I put into the system, and therefore the mole fractions will follow. But because we have only independent mole fractions for the C-1 components in the system, so that is why Xi provides an independent state parameter only for C-1 components, and the Cth mole fraction is not mathematically independent. Now let me talk about the phases. And this is because you remember components are actually abstract concepts, because when I talked about the components I showed to you the periodic system of the elements. I showed to you some symbols. And then when I talked about the system I told you, well, the system is defined by the number of components you take into account during your study. But at the end of the day we are studying three-dimensional real materials, their behavior. So we need something which is real, touchable, and three-dimensional. Now those are the phases. Actually, any system is made of one or several phases, and you should understand that any component which is dissolved in the system is actually dissolved in all those phases of the system. Now, what is, by the way, the difference between the different phases? The difference is hidden in the inner structure. So, in this picture, phase alpha and phase beta are different because they have a different structure. The number of phases in the system we denote as P capital. Its minimum value is obviously 1. Well, this is because if we have 0 phase, then there is simply nothing to study. It will be very important to understand whether we have 1 or 2 or 3, etc. number of phases in the system. But remember one thing, the maximum number of phases, P-max, which can coexist in the system in equilibrium, is limited by the so-called phase rule. The phase rule will be discussed later. Generally, the phases are denoted as phi, capital Phi, but if I want to make a difference between them, then I call them alpha or beta by small Greek letters. I also can use different states such as solid, liquid and gaseous, the first letters. So instead of alpha or beta, I can call a phase as S, abbreviated for solid, or L, small, abbreviated for liquid, or G, small, abbreviated for gaseous, which means a gas or a vapor phase. Now, because the two phases have different inner structures, that is why there must be an interface between them. At the beginning of this course, the role of this interface will be neglected, but this will be the true story only if all the dimensions of all the phases are at least 100 nanometer large or larger. In this case, the number of atoms or molecules along the interface will be negligible compared to the number of atoms in the bulk of each phase. And in this case, the result will be independent on the number of atoms in the whole system. However, later we will study equilibrium of nanomaterials. You remember, nanomaterials or nanosystems are those which contain at least one phase with at least one of its dimensions below 100 nanometer. In those cases, interfaces will play a significant role. They cannot be neglected anymore, and in those cases the equilibrium state will be dependent also on the number of atoms in the system. That we will consider much later. Now, how can you specify your phase? In the easiest way, you should give the amount of matter in that phase. So n small is an amount of matter in mole, and the phi is for the given phase. Now, it's obvious that if you add all the amounts of matter in all the phases in the system, then of course you end up with the total amount of matter in the system n. Okay, so n equals sum of n phi by phi. But previously we have seen a similar equation, and we found that we can also do the same with ni. And it's quite obvious, you know, the inventory of the amount of matter can be done in two ways. It can be calculated or counted through the all components and also through the all phases. You must obtain the same result if you don't make a mistake. And now we can define the so-called phase ratio, meaning what is the ratio of phase beta in the system or phase alpha in the system. But before I do that, let me give to you a very simple example to show how important is that from point of view of the functional properties of that system. Let me consider a two-phase system made of an aqueous solution and sand particles, silica particles. And let me consider two extreme cases. In the first extreme case, the majority of the system is made of sand particles, and that system is called a desert. Of course, a desert also always contains some water, but it's very difficult to find, and its functional properties are mostly determined by the fact that mostly it is made of sand particles. Another extreme is the ocean. The ocean is mostly made of water, but well, it might contain some sand particles, okay? But obviously, the functional properties of ocean are determined mostly by the fact that it's made mostly of water. Now, I showed you two different systems, desert and ocean. Both of them are made of two phases, water and silica particles or sand particles. These are the same two phases, and nevertheless, it is obvious for all of you international students how different they are in all their properties. And that is why the phase ratio should be defined, because ocean and desert are different only in the ratio of those phases. So the phase ratio is defined as the amount of matter phi divided by the total amount of matter in the system. And of course, if now I sum up all the y phi values, then I end up also with 1. Because the sum of all the parts in the whole is always 100%. By the way, let me note that I want to avoid you confusing mole fraction with phase ratio, and that is why mole fraction of a component I denoted through xi, but the phase ratio of a phase I denote as y phi, okay, to make sure you never confuse them. Now, from the last equation, we have again a very convenient rule, and this is that if we have a p-phase system, then it is sufficient to know to calculate in a quite difficult way, by the way, the phase ratios of only p minus 1 phases. And this is because the phase ratio of the last phase, the pth phase, follows simply as 1 minus the sum of all the others. For example, if we have a two-phase system, alpha and beta, then this last equation becomes y alpha plus y beta equals 1, and from here you can easily express y alpha as 1 minus y beta. So if you calculated or measured in a difficult way that the value of y beta is 0.6, then you can easily calculate the phase ratio of phase alpha as 1 minus 0.6, which is, of course, 0.4. Now, it's also obvious that if in the system you have only one single phase, then, of course, its ratio is not a problem, because by definition it must be 1. So, when we will discuss how to calculate the equilibrium in one-phase systems, then we will not discuss at all how to calculate the phase ratio in one-phase systems, because we will just remember that by definition the phase ratio of the only single phase must be 1. Now, in the previous slide I also mentioned state parameters, and it would be nice, of course, if the phase ratio would be also a state parameter, meaning I, engineer, can define what should be the phase ratio of which phases. But unfortunately, this is not the case. Unfortunately, this is not in my power. Because after I decided the value of pressure, the value of temperature, the values of all independent average mole fractions of all the components, now then anything what relates the question of phases is not a state parameter anymore. It doesn't depend on my wish, it depends on the laws of nature, including, of course, how many phases we have, which phases we have, and what are the phase fractions or phase ratios of those phases. Now let me show to you different phases, gaseous, liquid and solid. Actually, you studied them in school, obviously. By the way, we have also the fourth state, which is the plasma state. That's nothing else as ionized gases, but we will not discuss them in detail in this course. So let me explain how gaseous, liquid and solid phases differ, but this time when I talk about solids I always mean the crystalline solid phases. So first of all, the crystalline solid phases has obvious ordering at the atomic or molecular level. This is called SRO, which is an abbreviation for short range order. So you can imagine how the crystalline lattice looks like, and then the atoms in the real or close to real crystal are situated very similarly. Also, the crystals have their own volume and also they have their own shape. So for example, if I have a cubic crystal, then even if I take this cubic crystal and if I put it into the cylindrical container, then the solid cubic crystal will not be cylindrical and it doesn't care about the shape or the volume of this container at all. This is because it has its own volume and own shape. Now if I melt this crystal, then I get a liquid. Well, the liquid has still its own volume, but it doesn't have its own shape. It is because liquids flow under the influence of gravity, and this is something which the solid crystal cannot do. It cannot flow under the influence of its own weight, just under gravity. But because liquids flow under the influence of gravity, they are usually situated, at least along the surface of the Earth, in the bottom of a container, and they take also the shape of the bottom of that container. And this is because they are not ordered, and this is because they have empty vacant places. So there are certain places in the quasi-crystalline lattice where there is no atom, so there is an absent atom, and through those vacancies the flow of the liquid can be materialized. By the way, that is why liquids don't have the short range order, but deep science can show that they have some long range order called LRO. Well, dear international students, you can look very carefully at this picture, but if you don't see any long range order, well, that's not your fault. Now, what if we evaporate the liquid? Then we have a gaseous phase or vapor, which has no ordering, no own volume, no own shape. No ordering means the gaseous phase has no structure at all. That is why in one system we have only maximum of one single gaseous phase. Because it has no structure, so any gaseous component can be dissolved in the same phase. This is not true, by the way, for liquids. You can have different liquids which are not or very little soluble in each other, and of course we have many solid crystalline phases which are different from each other. Okay, coming back to the gaseous phases, they don't have their own volume and their own shape. It means they just use the volume and the shape of any container provided. Let me also explain the concepts of fluid phases. We call fluid phases the gases and the liquids together. The major property of fluid phase is that they can flow, and in contrary to the solid crystal, which cannot flow, at least under the influence of its own weight. Another concept is the condensed phases. We call condensed phases together the liquid and solid phases. Condensed phases are those which can be obtained from vapors upon condensation, and then depending on the temperature of condensation, whether it is lower or higher than the melting point, you can get crystals or liquids. Now, as I mentioned, we have many different crystal structures. I am showing to you two simple ones, face-centered cubic and body-centered cubic. The abbreviations are FCC and BCC, and those abbreviations will be frequently used instead of phi. You remember phi is a symbol for a given phase, so phi can be alpha or beta, or S for solid, or more specifically, it can be FCC, or it can be BCC, and many others, of course. Finally, let me explain that the solid phase is not necessarily crystalline. In nature and even after technologies, we often find so-called amorphous phases. The amorphous phase has of course its own volume and own shape, but it doesn't have its own short-range order, so it doesn't look like this crystal. It looks rather like a liquid. At most it has a long-range order. Amorphous phases actually form upon cooling from a liquid due to very high viscosities of the liquid. And this is because the cooling rate is so fast that the atoms or molecules have simply no time to be arranged according to the crystalline order, and then they remain in this quasi-liquid state. As a result, the packing of the crystal is always better, more economic. The packing efficiency is higher for crystals compared to amorphous solids, and that is why average two neighboring atoms or molecules are closer to each other in the crystal compared to the amorphous state, and that is why the cohesion energy is stronger in the crystalline phase compared to the amorphous solid phase, of course under the same composition, under the same temperature and pressure. And that is why, as we'll see later, the molar Gibbs energy of crystal solid phases will be always more negative compared to the amorphous phase of the same composition, pressure, temperature, and that is why in this subject cathode we are not able to calculate an amorphous solid state as an equilibrium state. So if we calculate a solid phase and equilibrium phase, it will be always one of the many possible crystalline phases, but it will never be the amorphous phase. Well, you can consider it as a limitation of cathode, but in fact this is not a limitation, this just reflects physical reality. This only means that indeed the amorphous solid phases are non-equilibrium phases which exist only due to transport limitations, only due to the fact that the viscosity of the liquid is too high, and during the production the phase is cooled with a too high cooling rate, which did not allow crystallization. As an example, let me show to you the standard states, the standard phases of the elements. So that means in which phase the elements appear in equilibrium under standard conditions, and the standard conditions by definition are 298.15 Kelvin of temperature and 1 bar of pressure. So in this periodic table for each element some abbreviations are given. The abbreviations are explained below. Altogether 17 different phases are given. Most of them are crystalline phases. But we have also gas. We can talk about one atomic gases, which are the noble gases, and we can talk about the two atom gas molecules such as nitrogen, oxygen, fluorine, chlorine, and by the way hydrogen. And we have also two different liquid phases, the metallic liquid mercury and the molecular liquid for bromine. The same information is given here. I list in the first column those 17 phases, and in the last column I am giving those elements which belong to those 17 phases. And by the way, I also mention here the structure in the German-based abbreviation, which is still even in English speaking literature is called Strukturbericht, which is a German word. This is because in the first part of the 20th century German science was still number one, and especially in crystallography, so they were those who found for thousands of different materials the structural units, of course, this is an ongoing exercise, by the way, but in the beginning of the 20th century, so they also designed these A2, A5, etc. symbols for different crystal lattices. And so in the English-speaking Kalfad literature, we frequently see that a phase is given not like BCC, but rather as BCC A2, to make sure there is no misunderstanding. By the way, in the inorganic world, we have today 286 different inorganic crystal phases. Well, we can group them into 19 different chemical groups. The largest number of inorganic crystals we have in a group called intermetallic compounds. Intermetallic means compounds which are made from two or more metallic elements. Then the second largest group is made of elements. You know, in crystal phase we have altogether 14 crystal phase for elements, which is 17 minus the gas and minus the two liquids, which is 14. And then we have many oxides, sulfides, carbides, borides, silicides, arsenides, tellurides, chlorides, nitrides, antimonides, etc. Okay, in addition to these 286 crystal phases, inorganic, we have also one gaseous phase, and plus we have around 10 plus liquid phases. It's not really well defined how many different liquid phases we have. We count those which are not fully soluble in each other. If we add all those phases, the 286 crystals plus one gas plus 10 plus liquids, we end up with approximately 300 inorganic phases. You remember, if we engineers select the state parameters under which we want to study the equilibrium of the materials, which is the value of the pressure, the value of the temperature, and the values for the average mole fractions of the independent components. Now then, what is the task? The task is to calculate how many equilibrium phases we have and which phase we have, and now we actually will have to select those phases from the list of approximately 300 inorganic phases, at least if we work with metals, alloys and ceramics. Well, you see, this is a huge task to select those 1, 2, 3, 4, 5 phases from the list of 300 inorganic phases. But let me mention that compared to the problems of the polymer guys, this is kind of nothing, because if you want to calculate how many organic phases we have in the field of polymers, now we have a problem. Well, I don't want to say exactly that we have the infinite number of organic phases in polymer field, but practically speaking it is close to infinity. And that is why that in the Kalfad world we see very few works on polymers, and we see the majority of works on metals, alloys and ceramics. Now let me explain to you again that all the components which are present in the given system are dissolved in all different phases, in each phase which is present in the same system. In this picture I am showing, for simplicity, a two-phase system, alpha and beta, and also a two-component system, A and B. So you can see that both components A and B are present in both phases alpha and beta. But because the two phases alpha and beta have different structures, therefore components A and B we like or dislike in different ways the two different structures, the two different phases, and that is why the compositions of the two phases will be usually different, meaning that the mole fraction of component A in alpha will be different from mole fraction of component A in beta, and also different from the mole fraction of component A as average in the system. And of course the same is true for component B. Now, to characterize a component in a phase, we should write its amount of matter using a double symbol I phi, meaning Ni phi, meaning amount of matter of component I in phase phi. Now, because of this double symbol, we can sum up these Ni phi's in two different ways. First of all, we can sum up according to the phases, and then we get the total amount of matter of component I. For example, if I want to know how much component A we have in the system, then I take the amount of matter of component A in phase alpha plus the amount of the same component A in phase beta, and the sum of the two will give to me the total amount of matter of component A in the system. Now, the second way, I can sum up also according to the components, and then I will get the amount of matter in that phase. For example, consider phase beta. Let me add the amount of matter of component A in phase beta plus the amount of matter of component B in phase beta. Obviously, I will get the total amount of matter of phase beta. Now, I can also define the mole fraction of component in a phase, similarly as I did before for the average mole fraction of the same component in the system. So xi phi equals ni phi per n phi. So I actually take the ratio of the amount of matter of given component in phase phi and divide it by the amount of phase phi. And of course, as usual, if I sum up all the mole fractions of component I according to all components, I get 1, simply because if I add all the mole fractions of A and B in the given phase beta, I should get 100%, which is 1. Now, this rule again leads to a very convenient situation, because for a C component phase, it is sufficient to calculate the mole fractions of only C-1 components. And by the way, that calculation will be quite difficult to calculate the equilibrium mole fractions of the C-1 components in the given phase phi. But fortunately, at least the mole fraction of the C-th component, can be found by a very easy way as 1 minus the sum of all the others. For example, if the given phase contains two components A and B, that means that this latest equation is written specifically like xa phi plus xb phi equals 1. From here, xa phi equals 1 minus xb phi. So xb phi, suppose we calculate in a very, very difficult way that this is 0.3. Then xa phi follows in a very, very simple way as 1 minus 0.3, which is 0.7. Now here I have two boundary cases. The first one is true for one-component systems. In this case, the mole fraction of that single component in all phases is 1 by definition, simply because there is no second or third component. And that also means that during our calculations, this will be not a question how much is the equilibrium mole fraction of the single component A in a one-component system in different phases, because we know in advance that it is 1 by definition. Another boundary condition is a one-phase system, meaning here in this picture, suppose there is no beta phase, so the whole system is made only of single phase alpha, and in this single phase alpha or in the same system we have of course the same composition of A, so that is why xi phi equals xi, simply because in this case, due to the presence of only a single phase, the components are not redistributed between the different phases. Now finally, let me mention regarding the composition or the mole fractions of different components in different phases, that because this is also a property of a phase, because this is actually the phase composition what we are talking about, this is also one of the tasks to be found to be calculated during the Kalfad method. So if the engineer defines the state parameters, which is pressure, temperature, and the average compositions, then the engineer should calculate the number of equilibrium phases, their identities, their phase fractions, and their compositions, meaning all the mole fractions of all the components in all the phases equilibrium. By this time in this lecture, you might be a little bit confused. During this lecture, I was giving very simple definitions. It was not a problem, I think. The problem is that I made too many of such very simple definitions, and that is why by this time in this lecture it might be confusing. Now if you feel so, please go back, start again, make notes to make sure you don't confuse different quantities with each other. But let me now make a connection between those different quantities in the so-called material balance equation. This follows from the so-called law of conservation of mass. I hope you remember Lomonosov and Lavoisier established that law a long time ago. In this subject I usually call it the law of conservation of components, which is the same story. It only means that in a closed system components do not disappear, they are not lost, and also they don't appear from nothing. Components are only redistributed between the phases. So suppose I introduced component I into the system in amount of Ni, and if this system is a closed system, then this amount Ni will remain forever in the same system, but the question is how it is distributed among the phases. So Ni should be obviously the sum of Ni phi's summed up by phi. By the way, this is not a new equation. If you look back to the previous slide, you can find it as equation number 2. Now let me use this law of conservation of mass or law of conservation of components to derive a more complex equation, and for that first let me divide both sides of this equation by n. N is the total amount of matter in the system. You know, if I divide the two sides of the same equation by the same number, still the equality is held. By the way, if you like, you can simplify back. But I divide it by purpose, so the left-hand side of this equation is now Ni divided by n, and I hope you remember it is Xi, the average mole fraction of component I in the system. So now let me rewrite the left-hand side of that equation as Xi, and then the right-hand side will be sum Ni phi divided by n. Okay? And now let me use another trick. Let me multiply the right-hand side of the equation by the ratio of n phi to n phi. You see, I can do it because I can multiply always anything by 1. That doesn't change anything, and n phi divided by n phi is actually 1. But I will not simplify that. I did it by purpose. I did it because I want to find these cross effects, these cross ratios. First, I show n phi divided by n. Hope you remember it's y phi, which is the phase ratio of phase phi in the system. And the second of such cross term is Ni phi divided by n phi. We just defined it as Xi phi, which is the mole fraction of component I in phase phi. And now if I substitute these two latest equations into the previous one, I find the final result of this derivation, and this result is called the materials balance equation. I hope you see that this material balance equation connects in a single equation the three different concentrations defined previously. So this is the average mole fraction of component I in the system, the phase fraction of phase phi in the system, and the mole fractions of components I, the mole fraction of component I in that specific phase phi. The beauty is that this equation is true for all components I, although you remember we already had a connection between mole fractions of component I, another equation, which tells that the sum should be 1, and therefore the material balance equation holds a new information only for C-1 components in a C-component system. It doesn't mean it is not true for the CF component. It is true for the CF component. It just doesn't provide you any new mathematical information. Now we have a boundary condition for one-phase systems. If we have a single phase, then summation is not needed. The phase fraction of that single phase is 1 by definition, and then you end up with the equation that xi equals xi phi, so the average mole fraction of component I is the same than the mole fraction of the same component I in that single phase. By the way, this latest equation was already written in the previous slide as the last equation. Okay, now we have the materials balance equation which we derived in the previous slide, and now let me show to you how to use it as an example. We usually use this equation to calculate the phase fractions of the phases, and usually we do it after the mole fractions of the components in this phase are already found. In this example, I am showing to you a two-component AB and a two-phase alpha-beta system. As was mentioned during the previous slide, we have C-1 mathematically independent material balance equations, and C is 2 in our case because we have two components. C-1 is 2 minus 1 is 1, so I have one single material balance equation which I can use in this case for this two-component system. So I should select one of those components. It doesn't matter which one I select, so let me select B as an example. So therefore I rewrite this equation by replacing I by B. So I get xb equals sum phi y phi times xb phi. So this is the same equation as the general equation, but using B. And then let me remind you that we have two phases, alpha and beta, and that is why the summation relates to two different phases. So the summation provides us the sum of two terms. The first term, in the first term, phi will be replaced by alpha. So it is y alpha times xb alpha plus the second term. In the second term, the phi will be replaced by beta. So that will be y beta times xb beta. Okay, so this latest equation is nothing else as the first equation specified for a two-component, two-phase system. And now let me suppose that the three x's are known. What I mean? Suppose I know xb, which is the average mole fraction of component B in the system. Of course I know it because it is given, because it is the initial state parameter decided by the engineer. So this is easy to know. Well, I also suppose that I know the equilibrium mole fraction of B in phase alpha and the same in phase beta. Now these two are not that easy to know. This can be measured after the experiment if I take a sample from the two phases, or it can be calculated. During this course we will learn how to calculate them. But suppose these are known. And now the task is we should find the equilibrium phase fractions of y alpha and y beta. But you know that generally for two unknowns, which are y alpha and y beta, one equation is not sufficient. But I hope you remember that we have actually the connection between these two unknowns, at least for two-phase systems, which has been written before as y alpha equals 1 minus y beta. Now let me substitute this equation for y alpha instead of this value and rewrite the previous equation again. So then xb equals, instead of y alpha I have 1 minus y beta times xb alpha, and then the second term is the same. Now in this equation, supposing I know the values for the three x's, we have only a single unknown, which is y beta, so it is easy to express, and these are final equation. Y beta equals xb minus xb alpha divided by xb beta minus xb alpha. And then of course y alpha is easy because it's 1 minus what we just calculated. But if you want it to be more scientific, of course you can substitute the last equation into this equation of y alpha, and then after some reconstruction you can find that y alpha equals xb beta minus xb divided by xb beta minus xb alpha. Okay, so this is the way how we can get the two unknowns, the phase fractions of the two phases, if we know all the compositions. Let me show to you how it works on 3 examples. For that I am showing the 3 values of xb on a scale. So I selected xb alpha as 0.25, xb beta as 0.75. So whatever is in between as an average composition of the system, it will relate to the two-phase system. So xb should be in this interval between 0.25 and 0.75. Only in this case we actually have the two-phase system. In the first example I selected xb as 0.5. You see it's exactly in the middle of the interval. And then substituting these 3 axes into these 2 equations, we get that both y beta and y alpha equals 0.5. So the take-home message is that if I position the average concentration exactly into the middle of the interval, dictated by the particular compositions of phase alpha and beta, then I will have in the system 50-50 of phase alpha and phase beta, because the average composition is just in the middle. And actually because the materials balance equation is nothing else as averaging the mole fractions of different phases, and the weight of this averaging is of course the phase fraction. Okay, so that's why this big average will give to you just the middle value if you have 50-50 of the two phases. Now in the second example I use the same range of xb alpha and xb beta, 0.25, 0.75, but this time I position xb, the average mole fraction of b in the system, very close to that value for phase alpha. So I selected it like 0.26, very close to 0.25. Substituting, we find that in this case y alpha is 0.98, and of course that is why y beta is only 0.02, meaning that this system is made mostly of phase alpha, 98%, and we have just little amount of phase beta. So we can make a conclusion that if I put the average composition close to the one of the phases, then this phase will be the majority phase. Let me check it in example number 3 using exactly the same values for xb alpha 0.25, xb beta 0.75, but this time positioning this average xb close to the other phase, xb beta, selecting xb as 0.74, close to 0.75. Substituting to the equations, I get that this time y beta is 0.98 and y alpha is only 0.02. So obviously the system is mostly made of phase beta, and we have only a very small amount of phase alpha. So the rule is confirmed, and the rule is again that if the average composition is close to the compositions of one of the phases and is far from the composition of another phase, then the majority phase in the system will be the one to which the average composition is close. You know, this visual evaluation is quite important because, of course, engineers calculate and can substitute into different equations in a blind way, and then they get a number, and then the bad or weak engineer is always happy. But a good engineer is not happy. The good engineer is checking the results, trying to figure out whether this is a reasonable result or not. Okay, for example, if I see this picture And by the way, similar pictures we will see later in two-component phase diagrams. On X we will have actual XB, on Y-axis we will have temperature, we will have different lines, I mean solidus, liquidus, etc., which will intersect at given temperature, these XB alpha and XB beta values, and then XB actually will be given, by us initially, by us engineers, because XB is the state parameter here, initial parameter. And now if I see such a picture, then in my mind I am sure, without and before substituting into those difficult equations, I'm sure that the result expected is anything between 0.9 and 1 for the Y alpha value, because XB is close to XB alpha and XB is far from XB beta. And indeed, if I get 0.98 as a result of this substitution, I say, okay, I am happy. But if I got, for example, 0.5, because there is some mistake somewhere, then I say, no, I'm not happy. Of course, I got a number, but a number is not good enough for this picture. So then I start checking and start finding the mistake. And actually, the same trick I am doing when I am checking the homework of my international students. I am not recalculating everything after you because I don't have that much time. I'm just looking whether your results are reasonable or not. So if I see this picture and if you tell me that Y alpha is 0.1, I say, wait a minute, I'm sure it's wrong. And you might be surprised how I know. So that's why I'm telling and that's why I'm teaching you this trick, because you should use as engineers the same trick. You should be able to evaluate the approximated real value, true value, even from looking at the phase diagram. And then if you go into calculations, you find the specific value, then you can check whether the specific result is reasonable or not. Okay, so we have so many different values in this lecture. Let me show to you how to calculate them in one example. For that, I give these 4 initial values. So let me calculate the case when the amount of component A in phase alpha is 1 mole, component B in phase alpha is also 1 mole, component A in phase beta is 2 moles, and component B in phase beta 6 moles. First, let me find the amount of matter in different phases. For that, we add the amount of matters of the components in the same phase. So, N alpha is calculated as Na alpha, which is 1 mole, plus Nb alpha, which is also 1 mole. So altogether in phase alpha we have 2 moles. 1 plus 1 is 2 for the whole phase alpha. Okay, let me repeat it for phase beta. Na for beta is 2, and B for beta is 6, so 2 plus 6 is 8. Okay, now let me calculate the amounts of matter for the components. Alright, now component A, we have it partly in alpha, 1 mole, and partly we have the same component A in beta, which is 2 moles. 1 plus 2 is 3. Okay, now component B, we have it partly in phase alpha 1 mole and partly in phase beta 6 mole. 1 plus 6 is 7. Good. And now from here, let us calculate the total amount of matter in the system. You remember we can do it in 2 different ways. So we can add first the phases. 2 plus 8 is 10, or we can add the components. 3 plus 7 is also 10, because the 2 ways provide the same result, 10 moles. I'm sure I didn't make a mistake here. Now let me calculate the average mole fractions of the 2 components in the system. First, I calculate for component A. For that I take the full amount of A, which is 3 moles, divided by the total amount, which is 10 moles, and then I get 0.3. Now for component B, I take the total amount of component B, which is 7 moles, and divide it by the total amount, which is 10 moles, I get 0.7. At this point, I can check one of our equations, saying that the total of the exercise must be 1, and indeed 0.3 plus 0.7 is 1, so this equation is obeyed. Right. Now let me calculate the mole fractions of the components in the phases. First, let me start with XA alpha, so this is the mole fraction of component A in phase alpha. For that I take the amount of matter of component A in phase alpha. Okay, it was actually given. It is 1 mole, so 1. And now let me divide it by the amount of matter of phase alpha, and alpha is calculated as 2. So 1 over 2 is 0.5. Okay, now let me repeat the same for XB alpha. The only difference is that I take NB alpha, which is by the way also 1. So in this case I get the same result of 0.5. And remember, we have a rule that the sum of all those values should be 1, and indeed 0.5 plus 0.5 is 1, so this equation is also obeyed. Let me repeat the same story for phase beta. First I want to calculate XA beta. You remember Na beta was given as 2 moles, and I divide it by N beta. Now N beta I calculated as 8. 2 over 8 is 1 over 4 is 0.25. Okay. Now XB beta follows as NB beta, which was given as 6, divided by N beta, which we calculated as 8. 6 over 8. I can simplify by 2, so it's 3 over 4, and 3 over 4 is 0.75. Again, this equation should be obeyed, meaning that the sum of the two must be 1. Indeed, 0.25 plus 0.75 is 1, so this equation is also obeyed. Now let me calculate the phase ratios of the two phases. First, the phase ratio of phase alpha is its amount, which we calculate as 2, divided by the total amount of matter in the system, which is 10. 2 over 10 is 0.2. The same for phase beta. We take N beta, which we found as 8, and I divide it by the same 10, which is the total amount of matter in the system. I get 8 over 10, 0.8. And you remember we also have a rule that the sum of Wi-Fi's also must be 1. Indeed, 0.2 plus 0.8 provides 1, which is okay. Finally, let me check the material balance equation, and let me check it for both components, separately for A and separately for B. Although I am sure if it works for A, then it must work for B, but you know, better to check it twice. So let me start with component A. So XA average, we already calculated 0.3. So 0.3 must equal to the sum of the two products. So I start with Y alpha. Okay, Y alpha is 0.2 times XA alpha. XA alpha I calculated 0.5. So multiply by 0.5 plus we go to phase beta. So I take Y beta, you remember it's 0.8, times X A beta. Now X A beta is here, it is 0.25. Okay, 0.2 times 0.5 is 0.1. 0.8 times 0.25 is 0.2, and this is because 0.25 is 1/4, and 1/4 of 0.8 is 0.2. Now if you add 0.1 plus 0.2, you indeed get 0.3, so this material balance equation is obeyed for component A. Now let me check the same for component B. So the final result should be the average mole fraction of B in the system, which we calculated as XB 0.7. So this must be the final result. And again, in this materials balance equation, I have two terms, two products, because we have the two phases. So first I apply this equation for phase alpha. So Y alpha, which is 0.2, times XB alpha, which is 0.5 multiplied. Okay, first term. Second term is for phase beta, so Y beta, which is 0.8, times XB beta, which we calculate as 0.75. Now the first term, 0.2 times 0.5 is 0.1. The second term, 0.8 times 0.75 is 0.6. Add the two. 0.1 plus 0.6 equals 0.7. Okay, satisfied. You see, everything is very simple. Everything is like in the primary school, kind of. Okay, but don't confuse anything with anything, because if you confuse something with something, that will never work. So it's all very easy, but you should be careful. So again, we have a large number of different physical quantities defined during this lecture. Now let me make some ordering, okay? Rather, let me build a map for this course called Equilibria of Materials, or the Kalfad method. First of all, let me repeat those physical quantities which are the state parameters. Remember, state parameters are those which depend on the choice of the engineer, first, and second are those which have a significant influence on the equilibrium of materials. So the first such state parameter is C, which is the number of components selected by us. The second one is the identity of those components selected by us, which actually the chemical symbols of the elements or the compounds we selected for the components. Then temperature, its value can be selected by us. Then pressure, its value can be selected by us, and the average mole fractions of all the independent components which can be selected by us. Well, all these parameters we can select, we can dictate, we decide what we select, and all these have an influence on the final result, on the final equilibrium state. Now let me mention that actually we have some more state parameters, and we will discuss them later, not at the beginning of this course. So first of all, a possible state parameter is N, which is the total number of atoms in the system, at least in the condensed phases. But I already mentioned to you before that if N is large, so large that all the dimensions of all the phases in the system will be larger than 100 nanometer, then this N is not having any significant influence on the final equilibrium of materials. However, if in the final outcome we find also small phases, those which have the dimensions, at least one of the dimensions smaller than 100 nanometers, then changing this N will actually change the equilibrium state. So this is conditional, not necessarily true if N is a true state parameter. First we will deal with the calculation of phase equilibria or equilibrium of materials for micro or macro systems containing a sufficient number of atoms, so N will be first neglected. And only in nanotechnology, for nanoscience, N is significant. Additionally, we have fields. We have the gravitational field, electric field, magnetic field. All of them might be important, but at the beginning we simply neglect them. Now, the second important part in creating the map for this course is to list all those physical quantities which characterize the equilibrium state. These are the number of phases, the identity, the phase ratio, and the compositions, meaning the equilibrium mole fractions of all the components in all the phases. These parameters I cannot choose. I mean, unfortunately, I cannot choose. I would be happy to be such powerful that I can choose everything, but I cannot, because if I selected the state parameters which are listed here, then these parameters follow the laws of nature. Now, I use the expression equilibrium here, or equilibrium state, and now I should stop for a moment and explain to you what I mean. So first of all these values which I listed here, which characterize the state, they are time-dependent values, supposing the state parameters are fixed. For example, we can show as function of time the phase fraction of one of the phases, or the mole fraction of one of the components in one of the phases. These are usually continuous functions as function of time. Usually we have a certain initial value. Then when we start the experiment, so we set all the state parameters. When we start the experiments, then in the first period these values change relatively fast. And then after a while, well, actually sometimes after a long time, the value becomes constant and it doesn't change as function of time anymore. And that is usually called the equilibrium value. But saying the truth, it's a true equilibrium only if you try a second experiment under the same state parameters, when you create the initial state different, and then if it has a larger value than the equilibrium value and it comes to the same equilibrium value from the top, not only from the bottom, now then you can call it the equilibrium value. Now, of course, you can ask me how you can do it less or higher than the equilibrium state. Now, this is easy because when you set, for example, xi, you can add to the system initially different phases, those different phases containing different concentrations of the components, making sure that the average mole fractions are the same, but initially in different phases you might have different concentrations, higher or lower. Okay? So that is the meaning of the equilibrium state. This is what we are actually able to calculate in this course. But then you can ask me, okay, if this is the equilibrium state, is it really reached in the industry? And I can tell you with almost 100% of being sure that it is actually never really reached in the industry, or, well, industry might come close to it, but usually industry doesn't reach the equilibrium state. And the reason is that time is money. Time is money because all the costs are proportional to the time. And if you want to find a product like this, and it has some perfect properties, then you usually stop a little bit below. Even you can design an industry which stops the production here, because these might be the desired composition, for example. But nevertheless, one thing is for sure. If you have a certain initial value and you calculate under the state parameters the equilibrium value, then all the processes will go from the initial value towards the equilibrium value. So even if the industry doesn't really go to the end of the story, so the first step of understanding what is going to happen, the first step in materials design is this kind of equilibrium calculations when you calculate the equilibrium state. And then, of course, the second question is, which is also extremely important, what about the transport properties, what about kinetics, what about nucleations, the rate of nucleations, the rate of phase transformations, the rate of chemical reactions, etc. So how fast all this is happening. Now this is out of the scope of this course, Equilibrium of Materials, but I hope that my international students will learn or already learned a lot about kinetics and also transport phenomena. So if you put everything together in your mind, then you can get the full picture. So this subject is about the equilibrium value. Okay? And I am not putting here to this P, phi, Y phi, X, Y phi symbols, I am not putting the little words EQ for equilibrium, because in the whole subject, in the whole course, I always will mean equilibrium. But I needed to explain to you at least once what is meant. So the state, there are millions of states in between the initial state and the equilibrium state. They are all possible, but what we deal about is the calculation of the equilibrium state. Okay, now you can ask me, why is all this important? This is all important because the characteristic values of the equilibrium state actually determine all the properties of the material you produced. Plus, very important, is the morphology. So if you have more than one phase, then how the phases are related to each other, how they are positioned, what is the size distribution of those phases, what are the shapes of those phases, because usually from equilibrium calculations the shape and the size doesn't follow. Well, by the way, except if we work for the nanosystems. If we work for the nanosystems, then we get additional information on the morphology, but as I mentioned before, this is usually not the case. Now, it means that we also need the phase field modeling. What is the phase field modeling? This is a complex modeling. The first step is actually what we do here, the Kaptay type calculations, and then all what I mentioned before, diffusion, nucleation, phase transformation, etc., etc., growth of the phases, precipitation, dissolution phase, etc., everything is included in the phase field modeling. Okay? So now we have the properties, which are mostly determined by these equilibrium values. And then, why is it important? Well, this is important because we, engineers, produce materials because we want to sell them. Well, maybe not personally me selling them, but the company I am working for is selling those materials we are producing on the market. And then we sell it to the customer. And then, of course, there are two situations. The customer might be happy or the customer might be unhappy. And now you should ask yourself a question: when the customer is happy with our material? Well, the customer is happy if the properties of the material we are delivering is matching his or her expectations, because the customer expects some properties. Please don't expect the customer to know what the hell is phase ratio. No idea. Even don't expect the customer to know what is the phase. Okay? No. The customer wants properties. But the properties are determined by these characteristic values, and therefore we have this logical chain. State parameters determine the equilibrium state. That determines, together with morphology, the properties, and then the properties determine the happiness or unhappiness of the customer, and that determines how long you can work for good salary in that company. If the customer is satisfied, then you have a safe job. If the customer is unsatisfied, then we have a problem. Okay, now in this course of equilibrium of materials, we actually deal with these two first big boxes. So the relationship between the state parameters and between the characteristic values of the equilibrium state. There is another big scientific field, how properties are determined by these values. Which phases, how many phases, phase ratio, phase composition, morphology. That's, again, a big science here. And of course, we have a department of marketing who try to keep customers happy, unhappy, well, almost independent what we do. But I tell you by secret, whatever the department of marketing is doing, the customer will not be satisfied if his expectations on the properties are not met by our material. Okay, so coming back to these two lab boxes, this is our business. This is what we are doing in this course. Now you should understand that the easiest way to make a connection between these two boxes is measuring. What does it mean? Okay, we engineers make a decision how many components, which temperature, which pressure, which average composition. So we make this system, set the compositions, the temperature, pressure, and then start the experiment. Well, start the experiment meaning sit down and wait. Okay, wait because processes are going on, and then wait until equilibrium is reached. Now, how you know, by the way? Well, you can know only by making sampling, okay, at different times, and when you see that nothing is changing anymore, and by the way, the same result is obtained from the bottom and from the top, now then you can be sure this is equilibrium value. And then when you reached the time needed to reach equilibrium, then you cool very fast the whole system. You should cool very fast to make sure nothing changes during the cooling. And then you reach a temperature when all the processes are so slow that nothing is really happening. And if you reach that very cold state, then you can prepare your sample, and then you can analyze your sample using scanning electron microscope and X-ray diffraction, whatever. We have many techniques. And the purpose of all those analyses is to find how many phases we have, which phases we have, what is the phase ratios, and what are the phase compositions. And if one such experiment is ready, then it means, imagine we have an Excel file, imagine we have different columns in this Excel file, providing state parameters and providing the experimentally measured characteristic values of the equilibrium state, and these will be one row in your Excel file, which provides you with the information how the state parameters and the equilibrium state are interconnected. Okay, now you can ask me a question why I don't provide to you with this Excel file. It would be much easier, you know. Sure, it would be much easier. Saying the truth, I don't have such an Excel file yet, but of course we are working on it. But for this purpose, let me make to you, show to you a very simple calculation. So obviously, what we want the full information, and we have seen that we have 81 stable elements. That's why we have maximum 81 components in the system. So I want to know everything about this 81 component system. Now, how many independent mole fractions I have? 81 minus 1 is 80, because you remember the last one I can get as 1 minus the sum of the rest. Plus I have 2 temperature, pressure. So I have altogether 82 independent state parameters in this case. Now I have to make certain concentrations, selected temperatures, selected pressures, and suppose, just for the example, that I selected 100 different temperatures, 100 different pressures, 100 different mole fractions for each element, etc., etc., and then I make a variation of all those state parameters. So how many variations I have? Well, 100 to the power of 82, which is 10 to the power of 164. Well, a huge number. But now let me go on with my example. Let me estimate in a very optimistic way what is the measuring rate. So, being very much optimistic, I say that one person, HS is for Homo sapiens, one person per 1 day can perform one measurement. It is very, very optimistic, because what does it mean? You prepare your samples, you wait for the time of equilibration, then you prepare your samples, then you perform scanning electron microscopy, X-ray diffraction, etc., etc., etc. Then you write a report explaining what you have done and what are your results. Okay? And that, if that happens within 1 day as a job of one person, then I would be very happy. In fact, it takes much longer time, but this is an optimistic calculation. I presume we are very efficient. Now, how many Homo sapiens I have as my co-workers? Okay, let me be also mostly optimistic. Suppose we have 10 billion people. Of course, I remember we don't have 10 billion people alive today, but very soon, like in 10 years, we will have, okay? And then you can tell me, but sir, how you can arrange all your 10 billion people working on your project at the same time if we have people who are just born, people who are just dying, people who are just making babies, people who are, I don't know, sick, people who don't understand your language, people who are not educated properly, people who don't possess an electron microscope which is needed for the measurements. Yes, my dear international students, I know. We have millions of problems. But let me be optimistic, super optimistic. And now I calculate how much time I need for this project. So I have 10 to the power 164 experiments needed, and divided by the number of my co-workers, 10 to the power 10, because each of them can do one measurement per day. And then I get 10 to the power 154 days, which is 3 times 10 to the power 151 years. And at that point, you should remember what is the age of the universe, which is about 10 to the power 10 years, which is much less than the time I need for this project. So my conclusion, despite the fact that I was super optimistic, my conclusion is that this is mission impossible. What is mission impossible? It is mission impossible to find out, using measurements, the full data bank needed for material science, the connection between the state parameters and the characteristic values of the equilibrium state. That is why, ladies and gentlemen, we need a theoretical path. We can expect, again, in super optimistic way, that if we have an additional theory in addition to measurements, then probably we can go faster. Of course, for this theory, we need equations. But I have a good news. We already have, during this first lecture, which is actually on CALFOD, we already have the first equation. And I explained to you that this equation can be used to find the equilibrium values for the phase ratios of the phases. But of course, we need additional equations to find the equilibrium compositions of those phases and actually the number and identity of those phases. Those equations we don't have yet, but now we are going on, and very soon we will have all the equations what we need. Now we are pretty close to the end of this lecture, but before I finish, I want to make sure that each of my international students exactly knows how to calculate mole fraction from mass fraction and vice versa. And this because you remember that we actually start with measuring the mass of the components, and from the mass of the components we should calculate how many moles we have. So let me define the mass fraction of component I, okay, denoted as Cm, its mass fraction, and this is defined as the mass of component I divided by the mass of the sample. And the mass of the sample is nothing else as the sum of all the masses of the components. And of course, because there is a concentration, again a ratio or mass ratio or mass fraction, the sum of the mass fractions of all the components obviously comes to 1. Very similarly, we introduced before the mole fraction of the component, and these are quite similar equations, except that for mass fraction I use masses, for mole fractions I use moles. Now, in order to find the equation which is able to convert Cm into X or vice versa, I need to find a quantity which contains both M and N. And the easiest quantity is actually the molar mass, because you remember this equation. We had it several times during the previous lectures, which tells us that the amount of matter of component I is nothing else as the mass of this component dividing by its molar mass. And now let me rewrite this definition for Xi. This is Ni divided by N. Now let me replace Ni by Mi small per Mi capital. Okay. Divided by N, but remember N is nothing else as the sum of Ni's, so the sum of the same story. So divided by the sum of the same story. Okay, now this expression here is identical with Xi. Let me again use a trick. Multiply the expression by M over M, where M is a total mass. And remember, I do it to get some cross ratios. Indeed, Mi divided by M, I hope you remember, this is CMI. Okay? And the same story vice versa. So finally, I derive the connection between the mole fraction of component I and the mass fraction of the same component I, and for that the only new information I needed the atomic masses or molar masses of all the components. Well, obviously I can get it vice versa. If I know the mole fraction, this is the way how to recalculate it to the mass fraction. Let me show to you 3 examples. They are quite similar. All the 3 examples considers 2 components, which are A and B. In all 3 cases we have equal mass fractions of component A and B, 0.5 both. In all the 3 examples I consider the same atomic mass for component A, which is 27 gram per mole. By the way, this is the case for aluminum. But in the 3 examples I will consider different values for the atomic masses of component B. In the first example, I take 28 gram per mole, which is approximately the atomic mass for silicon. And in this case, if I substitute here, I get that the mole fraction of component A is 0.509, which is, by the way, pretty similar to the mass fraction of the same component, 0.500. And this result is obtained because the 2 components have similar atomic masses. To prove this to you, that it really matters how the atomic masses of the components differ, let me show to you the second example. Here I deliberately select the heaviest component, bismuth, with its atomic mass of 209 gram per mole. And if I substitute, I find that Xa is now 0.886, which is much larger compared to the 0.5. And this is because this time the atomic masses are quite different. Another extreme, I can select 1 gram per mole for Mb, which is characteristic for hydrogen, and if I substitute, I get Xa equals 0.0357, which is again very much different from 0.5. Please note that the whole possible interval for the Xa values under fixed CMA values of 0.5 is anything between 0.0357 and 0.886, and the difference between them is something like 20 to 30 times. What does it mean? Such a mistake would take place if you have no idea what is the difference between the mass fraction and the mole fraction. But now you will never make a mistake, of course, because now you know how to recalculate all these. By the way, these equations for simplicity are written for Xi, which is the average mole fraction of component I in the system, and it's written through the average mass fraction of component I in the system. But I hope you understand exactly the same equations take place also if I want to calculate Xi phi, which is the equilibrium mole fraction of component I in phase phi, which is dependent, of course, on the equilibrium mass fraction of component I in phase phi. Okay, so these two equations relate to both cases. Also, let me mention that sometimes in engineering we use the wording mass percent. What is mass percent? It is nothing else as 100 times the mass fraction. Also, sometimes we use the wording mole percent, and what is mole percent? It's nothing else as 100 times the mole fraction. Now we have seen how to recalculate different concentration units for components. But we have a similar problem also for phases. You remember from the material balance equation we can calculate the phase ratio in unit of mole per mole. Of course it's dimensionless, but we can also call it a molar phase ratio. But then if we want to check it experimentally, we have a problem, because checking experimentally meaning we can actually measure the diameter, for example, of a spherical phase from the cross-section in the electron microscope, and from that diameter and from the size of the other phases, what we can calculate only the volume fraction of the phases. Moreover, if we want to estimate properties of multiphase materials, very often we find that if we calculate or estimate those properties, that volume fraction is a very useful unit, because in volume fraction the majority of the properties are more or less additive, while in molar phase fraction they are less additive. So let me then define the volume fraction of phase phi. The volume fraction is actually small phi. So this is defined as V phi per V. V phi is the volume of the given phase phi in cubic meter, and V is the total volume of the system, which is nothing else, of course, than the sum of the volumes of the phases. And obviously, because this is the fraction or ratio again, so if you add the volume fractions of all the phases in the system, then obviously you come to 1 again. Now, by the way, we had very similar equations when we defined this phase fraction, which now we can call molar phase fraction for clarity. The only difference between these two sets of equations is that, of course, the molar phase fraction was defined through the moles, while the volume fraction of phase is defined through the volume. And now the task is to make a connection between these two quantities, so to make sure we can easily recalculate them. For that we need to find a quantity which contains both n and v, or n phi and v phi, and this is the so-called molar volume of the phase. Vm is molar volume, Vm phi is the molar volume of phase phi, which is defined as the ratio of the volume of the phase to the amount of matter in the phase, cubic meter per mole. The physical sense is how much is the volume of 1 mole of a phase. By the way, I hope you remember when we discussed in one of the previous lectures the ideal gas law, we already introduced this quantity. Now from here we can find the volume of a phase as its molar volume times the quantity of matter in the same phase. And now if I rewrite the definition for the volume fraction, like here, V phi per V, then I can replace V phi by Vm phi times n phi, like this. And then remember V is nothing else as the sum of the same, V phi, so I divide it by the sum of the same. So this expression is the same as the volume fraction of phase phi. And now let me use again a trick. Let me multiply this expression by n over n. N is the total amount of matter in the system. And remember, I am doing always this trick to get some cross ratios again. N phi per n, I hope you remember, it is Y phi, which is the molar phase fraction. Okay, and the same story vice versa. So finally, I derived the equation which connects the volume fraction of the phase with its molar phase fraction. And for that I need to know the molar volume of all the phases. And of course I can convert it, so I can also get the molar phase fraction as function of the volume fraction. Now let me show to you the example of calculations. I showed two different examples, but they are pretty the same. In both cases I am considering two phases, alpha and beta, with the phase fractions of, molar phase fractions of both phases 0.5, and the molar volume of phase alpha 10 cubic centimeter per mole. And the two examples are different in the molar volume of phase beta. In the first example I consider it 10.1 cubic centimeter per mole, and if I substitute these values here, then I get that the volume fraction equals 0.498, which is pretty close to the value of 0.500, which was the molar phase fraction. So again we find that if this property which we use in the equation is pretty the same for the two phases, like 10 and 10.1, then of course the volume fraction and the molar phase fraction have very similar values. But of course this similarity is gone if you select quite a different molar volume for phase beta. For example, if you select 30 cubic centimeter per mole, your result will be 0.25, which is now pretty different from 0.5. Okay. By the way, let me mention that sometimes we talk about volume percent of the phases. Now the volume percent of the phase is 100 times the volume fraction of the phase, and we can also talk about the mole percent of the phase, which is nothing else as 100 times the molar phase fraction of the phase. Okay, by the way, as I mentioned before, to use these two equations we need to know the molar volume of the phase. Okay, in the previous example you remember we needed only the molar mass, and the molar mass was discussed in the previous lectures widely, so that was no need to discuss it again. But this time I think I need to clarify how you can at least estimate the molar volume of the phase. In the first approximation, the molar volume of the phase is the average of the molar volumes of its components. This is the standard value. Standard means that this is the molar volume of phase phi if it contains only a single component I. And this averaging is weighed by the mole fractions of the same component I. Okay, this is an approximated equation. It's not truly, not 100% valid, because sometimes when you mix components you can get some little increase in volume or some little decrease in volume. That depends on the interaction between the atoms and the molecules in the solution, but that we will discuss later. Okay, and this difference is within 10%. So you can estimate the molar volume of the phase within 10% using this very simple way, and now the only question remains how you get the standard molar volume of component I in phase phi. But this I also showed before, so there is nothing else as the ratio between the molar mass of that component and the density of that component in that phase when this phase contains only component I. You know, the density is really the easiest physical quantity you can measure for any phase. For that you need to measure only the mass of the phase, and the volume of the phase you divide the 2 gram per cubic centimeter, you get the gram per cubic centimeter. So it's really easy to find in handbooks or in Wikipedia, and it's also easy to measure if you have a sample. So in this way you can obtain the standard molar volume of the component, and then substitute here you can estimate the molar volume of the phase, and if you have those values then you can make the recalculation as shown here. Okay, ladies and gentlemen, this is the end of lecture number 5. I'm of course very happy. I hope you're also happy. I thank you a lot for your attention, and I again make my big promise. If I am still alive, then I am coming back with lecture number 6. Thank you so much.